So chemical kinetics, the rate of a chemical reaction measures how fast the reaction produces products or uses up reactants. And so in this illustration, which I made disappear by accident, we've got a fast reaction. This room does not like my pointer. And a slow reaction. So here at time 0, the red and the blue things are coming together to make a green thing, and over here we've got yellowish green and blue making this some, I don't know what color is that, kind of reddish. So at the beginning there's no product. And here we are at like 16, 17 seconds or so. The fast reaction has 4 product molecules and the slow reaction only has 1. We go here, I don't know why they didn't just do 30 seconds. It's like 32 seconds. Now we have, 6 product molecules here and only 2 over here. This reaction is occurring at a much faster rate. Does that make sense? And so we get down here at 47 seconds. This one's done, right? And this one is not even halfway yet. It's just occurring slower. So if I don't forget, so help me remember, I do have a demo to show you later where we'll look at 2 chemical reactions where one's going faster than the other. So we need to define what we mean by the rate of a chemical reaction. Rate in general is some sort of a change in a given period of time. We're familiar with rates of speed. How fast were you going on the highway? 70 miles per hour. A distance change of 70 miles in a time period of 1 hour. So that's speed, change in distance over change in time. For the rate of a chemical reaction, we're going to measure this in terms of change in amounts of reactants or products divided by the change in time. Okay? So let's look at a simple gas phase reaction where we have hydrogen and iodine reacting to form hydrogen iodide. So change in concentration of the reactants is going to be negative. Remember that change is always the final thing minus the initial. So the concentration or the amount of hydrogen is going to go down as the reaction occurs, right? So the final concentration will be less than the initial, and so it's going to be negative. We always record reaction rates as being positive, just by convention. It's just less confusing. So reaction rates are always positive. So if we define the rate in terms of the change in the hydrogen concentration, we're going to put a negative sign. Oh, great. We're going to put a negative sign here. And we're looking at the change in the hydrogen concentration divided by the change in time. Remember that brackets around a chemical formula indicate that we're talking about the concentration of that species, generally in moles per liter, molarity, but sometimes we use it differently, but generally moles per liter. So we can define the rate as the change in the hydrogen concentration divided by the change in time. That's the final concentration minus the initial concentration divided by the change in time. So this quantity on top is going to be negative, and then we combine it with that negative out there, and we end up with a positive rate. We can also define it in terms of the other reactant, the change in the iodine concentration divided by the change in time. That's also going to be a negative quantity, combined with the negative in front gives us a positive rate. Any questions? We can define the rate in terms of the products of the reaction as well. Here there's only one product. As the reaction occurs, the product concentration increases, and so the change in the product concentration is going to be positive. So if we define the rate in terms of the product concentration is going to be a positive number here, not negative. So the plus there is just to emphasize that it's not minus. You don't have to write that in there. So we've also got a 1/2 in here. Because for every one hydrogen molecule that gets used up, we're going to get 2 hydrogen iodide molecules. So the hydrogen iodide is produced twice as fast as the hydrogen is, I lost my words. Destroyed, decomposed, I don't know, gone, going away. Get fancy. This is increasing twice as fast as either of these are decreasing. And so to make the rate the same, we need just to say this is the rate of the reaction. We don't want the rate to be different depending on what we're looking at. We just want one rate. So we're going to put 1 over the coefficient out here to account for that so that the rate is the same no matter what we're measuring. We react 1 hydrogen and 1 iodine, and we end up with 2 of these. So for every 1 of these that goes away, we get 2 of these. The rate of the product is, the concentration is increasing twice as fast as the reactants are decreasing. So that's why we get this 1/2. It's this coefficient, 1 over that coefficient in front. Here's a figure from your textbook. Shoot. The Wi-Fi in here is not very good today. So that looks a little scary, right? That graph. It's okay. So what we have here is we have concentration in molarity, moles per liter, as a function of time in seconds. And for kinetics, we typically measure time in seconds, not in minutes or hours or anything else. We usually use seconds. So we're looking at the hydrogen iodide concentration here in the red line, and the hydrogen concentration. And so we see that as time goes on, the hydrogen concentration decreases and the hydrogen iodide concentration increases. But if we look at the slope at any given point in time, that represents the rate at that particular time. The slope of this line is twice that of this one. The hydrogen iodide increases twice as fast as the hydrogen decreases because of the stoichiometry. Everybody okay with that? Now, the rate of the reaction changes all the time because the rate of the reaction is often dependent on the concentration of the reactants. As the reaction proceeds, the concentration of the reactants changes, and so the rate changes. This can be really, really annoying. But here we have a table showing some data. So as time is going on, here's our hydrogen concentration, and that's going down. So that's what we expect. If we calculate the rate, the change, negative change in hydrogen divided by the change in time. So here this negative 0.181 is the difference between these two numbers, and divided by the change in time, there's the rate. As this proceeds, we see that the rate gets smaller and smaller and smaller because the reactants are going away. Eventually, it'll get to 0 because there's no reactants left. So the rate decreases as the reaction progresses. We can talk about an instantaneous rate. That's a rate at a given point in time. And that's what we're showing on this graph. So to find the rate here, it will be the slope of a line that is tangent to the curve at that point. It doesn't stay. See, the slope of this line is continuously changing. The slope gets less and less and less. That's the rate of the reaction decreasing. But we can measure the rate at any given point in time by drawing a line that's tangent to the curve and finding the slope of that line. So here we're looking at, remember, slope is rise over run, so the change in the height, change on the y-axis, divided by the change in the x-axis. So we can generalize the reaction rate definition for a generic reaction. So here we've got AA plus BB forming CC and DD, where these lowercase letters represent the coefficients of the balanced chemical reaction, and the capital letters represent the formulas for the elements or compounds. So we can say that the rate of this reaction is negative 1 over A, that's the coefficient here, times the change in the concentration of A divided by the change in time. Or for the other reactant, negative 1 over B times its concentration change over change in time. When we look at the products, these are positive now, because we always want the rate to be expressed as a positive number. So 1 over C, etc. If we know the rate of change of one of the species, we can figure out the rate of change of any of the others, because they are related to each other by that rate definition.
If there's no coefficient, do we just not put the one?
That's a good question. What if there's no coefficient? No coefficient is an understood 1, right? An understood 1 then would be 1 over 1, which is 1, and you can just leave it off. Yep. So sometimes it's confusing when you look at these and you see some of them have a fraction and some don't, and you're like, why don't they all have fractions? Well, because it's 1 over 1 and we just didn't write it. Chemists tend not to write the number 1 unless they absolutely have to. Any other questions? This allows us to predict rate of change of one species based on the rate of change of another at one point in time. It doesn't allow us to predict what's going to happen in the future. It's just a single point in time. So let's do a couple of examples. Consider this balanced chemical reaction. In the first 10 seconds of the reaction, the concentration of iodide drops from 1 molar to 0.868 molar. Calculate the average rate of this reaction in this time interval. So the rate of the reaction, we've got information about the I- concentration. So we're going to define the rate in terms of the iodide. So the rate is going to equal minus 1 over, and this coefficient here is going to go on the denominator. And then we've got the I- concentration. Whoops, I forgot the delta. It's the change in the I- concentration divided by the change in time. Defining the rate in terms of the I- concentration. So then we're going to look in here and see what information we have. In the first 10 seconds of the reaction, so that's going from 0 to 10 seconds, the time interval is 10 seconds. So we could plug that in. 10 seconds. Oh, it's 10.0 seconds. And then we need the change in the iodide concentration. So delta I- concentration. Yeah, it's having a fit. Come on. It says it's reconnecting. We'll try that again. So we've got the change in time, so we can plug that in here. So minus 1 over 3. Okay, it's showing this time. In the denominator, then we have the change in time, 10 seconds. And when things go screwy on the screen like that, or when I make mistakes, because I make them all the time, please tell me right away. It's a good thing. So the change in the iodide concentration, that is the iodide concentration at the final time, or at the second time, minus the iodide concentration at the beginning, right? So it says it dropped from 1 to 0.8. So the final is 0.868, and the initial is 1.00. I'm not always going to write it out like this, but we just need to be clear on what we're doing. You should have your calculator handy, because I screw up when I do math, and so you need to check me. So 0.868 minus 1. So that's negative 0.132 moles per liter. That's the change in the iodide concentration. So that's what goes in up here. And then we can put these numbers into our calculators. So I've got negative 1 divided by 3 times negative 0.132 divided by 10. And my calculator is telling me 0.0044, and I have some units involved here. I've got capital M, which is moles per liter, and I've got seconds down here. Nothing's going to cancel out, so I'm just going to write them all out. So this is capital M over S, or that can also be written as capital M times S to the minus 1. S. Finish the S. You can do it. No. Okay, let's finish this. I don't know what the recording is going to sound like. It could be really weird. Okay. Any questions about that? Yeah.
So now the 3I minus
Mm-hmm.
that we had the 1/3
Yeah.
for the product, that's the I3 minus. Would that just be 1 the coefficient? So
Oh, for this one over here?
yeah.
Yes. For that species, then this fraction would be 1/1. And because that's a product, then it would be plus instead. Yep. Any other questions? Okay, so same thing here. Determine the rate of change in the concentration of H plus. So the rate of change in the concentration is not the rate of the reaction. We're looking for delta H plus over delta T. So we just figured out that the rate of this reaction is 0.0, is it 2 zeros? Thank you. 0.0044 molarity per second. That's the rate of the reaction. We found that by defining the rate in terms of the I minus concentration change, but we can use this to find the rate of change of all the other species at this, over this time interval. So the rate in terms of the H plus concentration, well, H plus has a coefficient of 2. It's also a reactant, so it's decreasing. So we're going to have minus 1/2, 1 over the coefficient, times the change in H plus over the change in time. This piece right here is what we're trying to find, right? We're trying to find delta H plus over delta T. So we've got the rate is 0.0044 molarity per second, and that is equal to minus 1/2 times this thing that we want. So we'll do a little algebra. Multiply both sides by -2. So the change in the H plus divided by the change in time. We're taking this 2 and multiplying it by the other side, and then we're involving that negative as well. And so we're going to end up with negative 0.0088. And the units have not changed. We didn't do anything with units. Molarity per second. Any questions? You might be getting a clue. There's a lot of algebra in Chem 1B. A lot. So if you need some help with that, please ask. So any questions? I think there's a part C here. So predict the rate of change in concentration of H2O2 and I3 minus during this time interval. So this is very similar to part B. We're going to use the rate that we figured in part A again. And looking at the H2O2, the H2O2 has a coefficient of 1, so the rate is equal to minus 1 over 1 delta H2O2 divided by delta T. So then delta H2O2 divided by delta T, the rate of change in the peroxide is just going to be negative 0.0044 molarity per second. And what about the I3 minus? Do we really need to write all of this out for that? This has the same coefficient as H2O2. Both of them are 1. Anything with a coefficient of 1, its rate of change is going to be equal to the rate of the reaction because it's not modulated by a fraction. So what's different about the I3 minus rate of change compared to the H2O2? It's going to be positive. So this is decreasing at the same rate that that is increasing. So we can actually just write that out, delta I3 minus over delta T. That's just going to equal plus 0.0044. The plus sign there is not necessary. I put it there just to emphasize that this is positive, the other one was negative. Any questions? Yeah.
Can we plug in 10 for delta T?
We could plug in 10 for delta T, but what this is asking for is the rate of change. And so if you wanted to see just the change in the concentration, then you'd plug in the 10 and you'd get the change in concentration. But we're not going to do that here because they're asking for the rate. Good question. Anybody else? It's too soon for me to lose you, so if you've got questions, ask them. Well, how do we measure a rate of reaction? You know, you can measure the rate of speed, travel of a car in several ways. You can look at a speedometer, right, that measures how fast the wheels are turning and takes into account the diameter of the wheels and all of that. You can say, well, okay, this is the starting point, and then after 10 minutes, see how far did the car go, right, and then measure the distance and divide. Measuring reaction rates, there's not always anything that you can look at, and so it can be a little trickier. So what we're going to do is we need to measure the concentration of at least one component in the mixture as a function of time. So one of the reactants or one of the products. We don't need to measure all of them, we just need one. And there's two ways to approach this, and how you approach this is going to depend on how fast the reaction occurs. So if you have a relatively fast reaction, something that's going to be done, say, in less than about an hour, it's probably best to just continuously monitor the concentration. Some reactions happen over the course of several days, and monitoring continuously would be just really overwhelming. And so then it might be fine to sample the mixture at specific times and just get some data points that you could use. So the next question is, how the heck do you monitor the concentration of one of the chemicals in this reaction? There are a lot of different techniques, and these are all part of what's known as analytical chemistry, which is what I majored in grad school. It's all about measuring amounts of stuff and figuring out how much stuff is in there. And there's a lot of other ways. We're just going to mention a couple here. Polarimetry. This is a technique that measures the change in the degree of rotation of plane polarized light caused by one of the components over time. Some compounds are optically active, meaning that if you pass polarized light through them, they will cause the light to turn. The angle will be different, and that can be measured. Sugars do that. A lot of biological components are optically active. So that's one way that it can be measured. You can measure the total pressure of a gas mixture, because the total pressure will be related to all the partial pressures of the gases in the reaction. So in this example, our reactant and our products are all gases. If we allow there's a lot behind these. You have to take into account, you can't have the volume changing. You can't do this one in a beaker, right? Because the gases are going to escape. You need to do it in a closed container. But as the amount of products increases, because here you have 2 moles of gas and here you have 3 moles of gas, the pressure will increase because you have more gas. And so that can be measured. Another technique is spectroscopy, and we're actually going to do this in lab. Here, the amount of light of a particular wavelength that's absorbed by one component is measured over time. So you can find a certain wavelength that one of the components absorbs. And you can measure by passing, actually let's just go, I think I have a picture. There it is. A picture of a setup here. So you've got a light source, and we just want a narrow beam of that light. So we pass it through a slit, pass it through a monochromator so that we can choose one wavelength. We pass that one wavelength through the sample, and then we have a detector over here. As the concentration of the substance that absorbs that wavelength increases, then the amount of light that comes through to the detector decreases. And so we can monitor the concentration of that one component without messing up the sample or the reaction. It can just happen right there. This iodine and hydrogen works because the iodine is a colored gas, and so it absorbs light very nicely. So we take all that information out into a computer. Any questions? One of the things that I find fascinating about science is the problems that have to be solved. So you want to know something, and you can't just measure it. You have to figure out how to measure it when it's something that can't be measured directly. And so all of these different analytical techniques are, stuff that people came up with to measure something that you can't just take a ruler. You can't count the molecules, so you have to figure out other ways to measure these things. If you're doing periodic sampling, so a longer experiment, and you're just going to take samples at particular times. The word aliquot is a common word in chemistry. Come on, pointer. Pointer's gone. Oh, but no, it isn't. It's stuck now on the word aliquot. An aliquot just means a sample from the reaction mixture, just a little sample. So we can take samples from the reaction mixture at particular times and then analyze the samples. Of course, there's considerations like you don't want to take so much of the sample out that you screw up the reaction, right? It has to be a small percentage of the actual reaction. So then we do quantitative analysis. I don't know what it's doing. Quantitative analysis on those samples, and there are lots of different techniques that can be used for this. We can use titration. You pull the sample out and you titrate it to maybe find out how much acid is in the reaction mixture. Gravimetric analysis, where you'll use a precipitating agent to precipitate the substance of interest, or gas chromatography. Or we can use gas chromatography. We actually have a gas chromatograph in our instrument room. We have a lot of really cool instruments in there. And I'll just put in a plug for our lab tech certificate program. You guys would be eligible for that next year. You'll get to use all of those cool instruments. And it's a really, really neat program. So we'll be talking more about that later. But the gas chromatography, that can measure the concentrations of several different components in a mixture. One of the problems with mixtures is sometimes you can't separate them. And so the gas chromatograph separates the components. Here's a diagram. So use some sort of a carrier gas, and that gas flows through a column. It's actually a long, very long coil with a very small internal diameter. The gas flows through here, and then you take your aliquot from your reaction mixture and you inject it in here. And it gets carried along by that carrier gas, and the different components in your mixture will have varying amounts of attraction for the column. And so ones that are attracted to the column will kind of stick and lag behind, and the ones that are not attracted to the column will just shoot right through. And so then you've got some sort of a detector here, and as the gas comes through the detector, you've separated the components of the mixture, and so you can measure just one, or you could measure a bunch of them if you'd like. And so you get a signal like this over time, that here's one component coming out and there's another component coming out, and we can measure their concentration based on how tall those peaks are.